Okay, so today we start with the next topic, that is the mass spectra and the IR spectra. Mass spectra, you have already done it before, but just a quick review. Now, over here in Unit 2, when you're talking about the mass spectra, they are not going to talk about how the mass spectra works and all. You are expected to interpret the data. That's the main thing from the mass spectra. So just a quick review before we start using this. So when you talk about the mass spectra, it gives us an idea if you the number of isotopes. You can find out the number of isotopes and their relative abundances. And based on that, you can find out the relative isotopic mass of the any element if it has a isotopes. Then you can also find out the MR, that is the molecular mass of an unknown substance. And it also gives us, to some extent, it also gives us an idea of the structure of an unknown substance. Now, right now, we are going to focus on this. Number of isotopes, you know the number. How will you know the number of isotopes? Number of isotopes will be equal to the number of peaks. So how many lines you have, that gives you the, or that peaks, that gives you the idea of the number of isotopes. And you have done the calculation for relative isotopic mass. So I'm not going into that. Our main focus over here is, you are going to identify the organic molecule. You are going to identify the organic molecule MR. So you can identify the organic molecule also based on its MR. How you will do that? Now, first and the most important thing is, remember, the mass spectrometer, it identifies only positive ions. And we are already aware of that whole mass spectrometer. Inside of the mass spectrometer, how ionization chamber, acceleration chamber, then deflection chamber, they work and so on. That may not be asked in the Unit 2. There is more of interpretation of the data. Now, we can identify the positive ion. That's one thing. And the mass spectrometer, or I would say the mass spectra, this is the mass spectra of any substance. It looks like this way, where on the x-axis you have M by Z values, and on the y-axis you have relative intensities. Sometimes percentage, relative percentage, intensity, better word is relative percentage. So this is in terms of percentages. Now this is an important thing, M by Z value, where M is for mass and Z or Z, whatever you want to say, that is for the charge. At our level, at an AS level, by default, it is considered as +1. Otherwise, if they don't say anything in your exam, it means it is +1. But if the examiner wants any specific questions, then they may change this. That is why M by Z is important. So M by Z for us is similar to like M, that is a molecular mass, because we are considering this as a +1 charge by default. Now, first thing is, how are we going to get, let us say when you have a mass spectra, these are your M by Z values, and these are your relative percentage. Yes. Now, you may have some peaks like this, like here. So the maximum M by Z value, remember this thing, the maximum M by Z value is or represents the MR of the substance. the MR of the substance. Now, sometimes if the examiner wants, they may give you a line or a peak which is n plus 1. N plus 1 means, like for example, if this is 58, the small peak will be at 59, n plus 1. If the examiner wants to ask a question on this basis, then they will give you. This one, this is due to, so they will ask you, what is this peak due to? This is due to carbon 13. This is only what we should know. Every carbon has some amount of carbon 13, very less amount. So there is a very small peak, that is n plus 1, because carbon is 12, so one extra mass will be there because of 13. We need to know this for carbon 13. So right now, you know two things: maximum m by z value, that gives you the MR. The n plus 1 peak is due to C13, and the maximum height, that means intensity of the peak, it represents the most stable ion. Now the question arises, if this is due to the molecule, this is called as a molecular ion peak. That means this is your unfragmented molecule. Unfragmented means it has not broken down. So this is the whole molecule. That is why it is maximum mass. If your molecule is, let us say, like this, and it breaks from here or here, then what is happening? It is fragmenting, or better word is fragmentation is taking place. Now, if the fragmentation is taking place, each of these pieces of the molecule will have a lower mass. So we should be able to identify based on this the structure. So we will be able to identify based on the structure. Now let us say for example, so we will talk about the fragmentation after a while. Let us say I want to identify, they tell us there is a organic, and remember any of these organic analysis, basically they are not done in isolation. You have to bring other informations from other analysis. Like for example, let us say they say you have been given an organic compound, or let's say a hydrocarbon is given, X is a hydrocarbon. So I will try to teach this, explain it based on the taking an example. That makes it easier to understand. So X is a hydrocarbon, and then X reacts with bromine water, and there is no change in color. The first thing is what inference you get. Now this can be asked in your unit 3 also. Inference means what can you deduce, what information you can get about this. So now since there is no change in color, we know it is an alkane. That's the first thing. So right now we know X is a alkane because it was a hydrocarbon and there is no change in the color, so it is an alkane. Next thing they said that the mass spectra of X is given. Question number 1, identify X. Now you need to know exactly which compound it is. Is it methane, ethane, propane, butane, what? So let's say the mass spectra was given to us is percentage abundance. Let us say there is a peak at 58, then there is a peak at 43, then there is a peak at 29, and there is a peak at 15. First thing is, this is your maximum m by z value. So in this case, the maximum m by z value is 58. So this means this is your molecular ion peak, and you can find out the molecule from here. So right now, what information you have? That X is an alkane. X has a molecular mass of 58. So we will be able to identify what is X. Now we know the general formula for alkane is CnH2n plus 2. So what you will do is, you will take the molecular mass of this and it should be equal to 58. Like for example, if it was C2, then what you would have done? You would have done 12 plus 2 to get the mass. That is what I'm doing. Carbon mass is 12, so it is 12N. Each hydrogen is 1, so it will be 2N plus 2. That should be equal to 58. So 14N is equal to 58 minus 2. So 14N is equal to 56. So N will be equal to 56 over 14. This will be how much? 4. So this means your X is C4, H 4 into 2 is 8, 8 plus 2, 10. X is your this thing. That's the first thing. So this is what they have asked us. They have asked us to identify. The next question they could have asked us is, identify the species responsible for the peaks at all this thing 15, 29, 43, and 58. So they want us to know the peaks for this thing. Now this leads us to the concept of fragmentation, which I have given you an idea. Fragmentation, that means breaking. So fragmentation basically means you are breaking the molecule at different places. Now, whenever fragmentation takes place, when the fragmentation takes place, like for example, like this fragmentation, when I'm talking about, it may break from here, it may break from here or here. So right now we are focusing only on the carbon-carbon bond breaking. At a higher level, you may get other bonds breaking also, but not at this point. Now, when fragmentation takes place, whenever takes place, two species are made, two of them. And this is due to homolytic fission. Now, why there will be a homolytic fission over here? The reason for the homolytic fission will be the carbon-carbon bond. The carbon-carbon bond is non-polar. If this is your molecule and the molecule breaks from here, now this carbon-carbon bond is non-polar. So as a result, it will undergo homolytic fission. And we know when it will undergo homolytic fission, they result into formation of a free radical. So you will get a free radical like CH2, CH3 here, and CH2 with a free radical. So two species are formed. Then this may lead to formation of the positive ion. This may also lead to the formation of a positive ion. So usually when we are teaching, we don't say free radical is formed. We don't talk about the free radical because these are neutral species. These free radicals are neutral species and are not identified. So we usually skip this, but this is the process. Fragmentation results into free radicals, and then free radicals may form the positive ion and another positive ion. That would be the next step. So we focus on this part. We focus on this part that they will be identified. They will be identified. So whenever there is a fragmentation, we don't talk about free radicals being formed and then the free radicals they changing into positive ion. No need. We simply talk about the positive ions being formed because they are the ones that will be identified. Now, again, going back to our mass spectrum, which was given to us. This is a mass spectra that is given to us. So from here, we have been able to understand the first thing that it is a butane, but right now we are trying to focus on what are the other peaks due to. So the other peaks are due to fragmentation. So let's understand how. So main idea over here, you have to get these masses. You have to get these masses. So for example, your M by Z value was 58. So the species, now why they use the word species? Because we should know that they are always positive ions. So it is due to C4H10 plus. So this is your unfragmented molecule. This is your unfragmented. That means it has not broken down. Unfragmented molecule. Now let's look at the other things. So we have 4 carbon atoms. Let's say this way, all are hydrogen's atom over here. There is one question where they have talked about hydrogen breaking. Otherwise, the carbon hydrogen bond breaking. Otherwise, you don't need to look at that. Now, one possibility is the bond may break from here. Now, if the bond breaks from here, you will have this part, which will have a mass of 15, 12 plus 3. And this whole thing will have a mass of 12 plus 12 plus 15, which will be 29. And this whole molecule is 58. This whole molecule is no, I don't think this is 12 plus 12. No, plus 15. This will be 39. We are doing a butane. So this will be how much? 3. Okay, I'm taking 12. We have left the hydrogen atom. That's the reason why we are getting it here. It should be 14 plus 14 plus 12 and 3, 15. So we were ignoring the hydrogen atom. And again, that's a very common mistake. We just look at the carbon atoms and decide. So it is 14 plus 14 plus 15. That will be 5, 8, 3, and 4, 43. And 43. The total mass is 58. So this will give you a peak at 15. This part will give you the peak at 43. This is one possibility. The other possibility is the molecule may break. The molecule may break from here this way. If the molecule breaks from here, you will have this 29 and this is 29. Total is still 58. Then the other possibility is it may break from here, but if it breaks from here, it is still 15 and this is still 43. So it's the same as the first case. So now we know what are the species responsible. So if I write again over here, M by Z value and the species responsible, the first one was 58 and we know it is C4H10 positive. The second one was 43. Now 43 was this part. This part was 43. So this is C3H7. Remember to put positive either here or on this side. That does not matter, but it has to be a positive ion. Then it is 29. 29, we know it is 2 carbon atoms. So it is C2H5. You can count the masses. And the 15 is due to CH3. So this is the whole concept of your fragmentation. This is the whole concept of fragmentation and how to find out the species. The positive charge is very important because it is a positive charge. Without that, the mass spectra cannot identify. This is one thing. This is one type of question that can be asked. Now, another type of thing that can be asked to us is that there is an organic compound. There is an organics compound X. It has a molecular formula of let's say C3H6O. So they may ask us to identify it on the basis of the mass spectra. First thing is we know it is C3H6O. So this can be propanone or propanol because both of them are isomers and both have the same molecular formula. So it can be propanone or propanol. But the problem is they are giving us the mass spectra and then they are asking us which of this mass spectra is for propanol and propanol. So let us say I have been given two mass spectra, relative abundance or percentage abundance or intensity. This is one spectra where let's say there is a peak at 15. They may not give us all the peaks. Then there is a peak at 29. Then there's a peak at 43. And then there is a peak at 58. This is one mass spectra. And the other mass spectra is, so they may ask us to identify which of them is due to the propanol and which of them is due to propanone. Now, if you will observe over here, so this is the second spectrum. So I have to identify which mass spectra is due to propanol and propanone. So how are we going to do this? Again, if you look over here, usually the M by Z value could have helped us over here. Oh, this is M by Z, we know this, and relative abundances. So usually the M by Z value could have given us an idea, but in this case, both of them have a 58. The reason is these are isomers. So your C3H6 H6O has the MR of 58. So you can find out 12 into 3 is 36, 36 plus 6 plus 16. That will be 58. So we cannot differentiate between propanol and propanone on the basis of the M by Z value. So we need to look at the fragmentation. So looking at the fragmentation. Now, if it is a propanol, propanol means aldehyde. If it is a propanol, it would be this thing. So one peak will be due to this. So the M by Z value will be 58 for the unfragmented one. Then there is a possibility that it may break from here. Now, if it breaks from here, this has a peak because of 15 and 14, that is 29. So there will be a peak at 29. And this will be 12 plus 16 plus 1, that is again 29. So one possibility is this, you will have a peak, both of them, that means the ethyl group as well as the CHO group, both of them, they will give us a peak at 29. That is one possibility. The other possibility is the molecule may break from here. The molecule may break from here. Now, if it breaks from here, you will have 15, and this will be 29 plus 14, that is 43. So if it was a propanol, if it is a propanol, you will have a peak at 58. You will have a peak at 15. You will have a peak, 15 is because of this. You will have a peak at 43 because of this. And then you will also have a peak because of at 29 because of either of this. So you will have a peak because of, you will have a peak because of C3H6O positive. You will have a peak at 15 because of CH3 plus. You will have a peak because of CH3, CH2 positive, or if you want, you can write C2H5 plus, same thing. And then, no, there is one 40, for 43, you need one more carbon atom. This is for 29. The total mass is 29. So for 29, you will have the peak at C2H5 plus, or you can say CH3, CH2 plus. And for 43, you will have the peak at CH2, CHO plus. So these are the major peaks because of the propanol. Now, if you look over here, there is no peak at 29 over here, while there is a peak at 29 over here. This clearly means that this is a propanol, because you have a peak at 29, which is shown by propanol. But let us check if propanone can also give us a peak at 29. Sometimes they ask you which peak is not possible over here in propanone. So there is a possibility of this breaking from here. This is propanone we are talking about. We're talking about propanone. So this will give you the peak at 15, and this one will be 43, and the whole molecule will be 58. That is one possibility. The second possibility is the molecule may break from here. In that case, again, this part will give you 15, and the other part will give you 43. So in a propanone, you will have the peak at 58. That will again be due to C3H6O plus. Then you will have a peak at 43, which will be due to CH3CO positive. And then you will have a peak because of the peak at 15 because of CH3 plus. The peak at M by Z value of 29 is not possible for propanol. Whichever way it breaks, fragments, it is not possible. So this peak will be missing. So peak at m by z value of 29 is missing in propanol. This will be missing from here. So your mass spectra, this mass spectra is for propanol as 29 peak missing. M by Z value of 29 peak is missing from here. So that is how you are able to relate it. Sometimes the same thing can also be related to your identifying the type of alcohol over here. Like for example, they tell us that X is a organic substance. So this is related to your unit 3 also. X is an organic substance. Now when X is reacted with PCl5, there are steamy fumes. So what does this suggest about X? X contains the OH group. That's the first thing. The X contains the OH group. The OH group can be due to the carboxylic acid, which are represented as this thing. This is carboxylic acid. Or it is due to the alcohol, the OH. Remember, the reaction with the PCl5 is to identify the OH group. So both of them, they contain OH. So it means this X is not an aldehyde, this is not an ketone, not an ester, not ether, not any other organic compound. It is either the carboxylic acid or the alcohol. So you are able to identify this OH group is present in X from one of the tests. This test was given to us and you have to infer this, conclude this. Now, next thing they can say is X to the X. So this is now the second test. X, you are adding sodium carbonate, or they may say sodium hydrogen carbonate. There's two possibilities over here. Let us say the examiner tells us no bubbles were observed. If no bubbles were observed, it means it is an alcohol. If I'm saying, if there were bubbles, then it would be carboxylic acid. But let us focus on this thing. This was our aim, that when you are adding the sodium carbonate, there was no bubble, so it is an alcohol. Now the problem is the alcohol can be primary, it can be secondary, it can be tertiary. How to differentiate between them? So to differentiate between them, what you have to do? You have to take the help of oxidation of alcohols. You have to take the help of oxidation of alcohols. So that will bring us to the third test. They would say X is to X, you are adding potassium dichromate in acidic medium. Now there are two possibilities. Either the color changes from orange to green, or there is no change in color. Now that's easy. If there's no change in color, it means it is tertiary alcohol. Finish. Tertiary alcohols are not oxidized. So if they are not oxidized, there will be no change in color. But suppose there was a change in the color. So if there is a change in the color, it would mean it is either primary or secondary alcohol. So now we have to differentiate between them. So You started with from all organic compound, you came to the conclusion it can be carboxylic acid or alcohol. Then you were able to differentiate between them. There was no bubble, so you said it is alcohol. So from all the organic compounds, now you know it is an alcohol, primary, secondary, or tertiary. And now from all the alcohols, you are able to know that it is primary or secondary, not a tertiary. So I want to now differentiate between primary and secondary. Now there are two ways. There are two ways they can ask from here. One way is you identify based on the oxidation product. Oxidation product means when you have oxidizes, what is the result? So that means oxidation product can form an aldehyde or it can form a ketone. And how do you test them? Using the Tollens reagent, Fehling solution. We have done this before. Fehling or Benedict solution. So if it is a Tollens, if it is an aldehyde, Tollens reagent will give you a silver deposit. Here nothing will happen, no change, no change. For ketones, there will be no change. For Fehling solution, you will get a red precipitate. For aldehyde and ketone, here there is no change. So one way is they could take you to the chemical analysis. The other way is if you want to differentiate between them, they will give you the mass spectra. Mass spectra is given. So you will use this to identify. Let us say the mass spectra which is given to us is this. This is 58. This is 29. This is 15. And then this is 43. So they may ask you to identify X. Now here it is 58, M by Z value, maximum, M by Z value. So, and it can be an aldehyde or it is an alcohol. No, there is no need for, I don't think there is a need for 43. Let us see. So what you will do, we know it is an alcohol. So alcohols have the formula for CnH2n plus 1 OH, that is equal to 58. You are doing the oxidation product. So oxidation product can be an aldehyde or a ketone. Remember, oxidation product of an alcohol, primary or secondary, it can be an aldehyde or a ketone. So in this case, we have just done few minutes back with a 15.8 M by Z value, it would be C3H6O. Now I need to find out, is this for aldehyde or for ketone? So we have done few minutes back that the peak at 29, so I'm not repeating it again. I have explained over here. With propanol, the peak at 29 will be missing. Now we see over here that there is a peak at 29, which clearly means that it is an aldehyde. And based on the 58, we know it is propanol. It is propanol. So if the oxidation product is propanol, that means X, which was supposed to be an alcohol, it will be propanol, which is a primary alcohol, because primary alcohols are oxidized to propanol, to aldehydes. If suppose we got it as a propanone, then we would have said it is a propane 2-ol. That would have made it a secondary alcohol. So this is all about your mass spectra. Next video, we will talk about IR spectra.